All right, the motor force, a little bit more detail on it. We're going to analyze why it works instead of just sort of trusting the right-hand rule, left-hand rule stuff. And then we'll see how it gets used in electric motors, because if you're talking about the motor force, well, what are we going to make with that? Electric motors, right? So the motor force, just a little review. We would have seen this as, if you had a north and a south facing this way, and if you have electrons, I can use my left hand. So I'm going to have my thumb pointing into the page. I'm going to have my fingers extending down from north to south, and we're going to say, okay, we're going to have a push to the right? So this is the picture that you should be looking at with this kind of thing, right? So you have your thumb and your fingers. Now these aren't the same direction as these guys here. Let me just pause for a sec here. All right, just paused quick there to get my touch screen going here. But if you slightly better artistic skills here, so if you had your left hand, your thumb pointed in the direction of the electron flow, and then we had our fingers pointing down. Rotate this guy a little bit. Fingers pointing kind of down this way, whatever, right? So picture that. And then you have the palm of your hand pushing that way, right? So I can't see any of the fingernails. There's like a tiny fingernail on the top of my thumb, I suppose. If you're holding your hand like that, your fingernails are on the back side of all of these fingers, right? So yeah, so a push to the right. In this case here, same deal, right? This side, this one here, into the page, the thumb, fingers pointing straight down, the push is to the right. So there's our hand rule for getting the direction of the motor force on those guys. Again, the direction of current positives or electrons with the left-hand rule, right? And finger stretched out and so on, you get your push in the direction of the palm, right? Well, to analyze this a little bit more, let's analyze like why this happens. So we're going to draw in magnetic field lines due to the current in a carrying conductor. So this one here involves the left-hand rule, where we would have the thumb pointing in the direction like this here. So let's say, okay, there's my thumb with my fingernail on my thumb, and then I'm going to have my hands curled like this to show like this, right? So my hand is kind of curled like that, if you will. I don't know. It's like, it has to go like that for my wrist, I guess. And I have my fingernails here, so you can really see what's going on there for that drawing. Hopefully, not the best artist, but so the yeah, it's a little hard to tell, but I have to rotate this guy a little bit, like as a whole here. The fingers, the up with the fingers is up on this side here, right? So this up. I might have to redraw that one, but I mean, yeah. So this is this right here, right? So this up idea here. So let me group this guy together a little bit. Redeem myself here. Anyways, yeah, like you have to just extend the thumb a little bit more out. Like I don't have my thumb pointed out enough, right? So there we go. So thumb pointing this way, and then my fingers are wrapped and so on. And yeah, so a little bit more of a visual of that up on this side, and going around and up like this, around and up like that, right? Anyway, so that's the magnetic field direction of that thing. A little easier maybe to visualize here, just thumbs straight into the page, and your left hand, because we're talking about electron flow here, right? Your left hand would curl in a counterclockwise direction. So we got that one. And then let's also draw in the next one here. Second, let's draw in the magnetic field lines of the magnet itself. And so they're just away from north to south like that. And so we look at this and we can analyze this and say, okay, well, what's going to happen then? And so the analysis is that we have likes right here and we have opposites right there, right? What happens with like magnetic fields and opposite magnetic fields? You know this, right? So what we have is, I don't know if I have it written out on a page or if I'm just doing it in person. Here, doing it live. I think I've got it written out. Yeah. So we have likes here. So we get a repulsion and we get an attraction here. And so really you've got, both of them are pushing to the right. So we get that same analysis. So a lot of these hand rules are, nice results. So they're used as a way to just do this conveniently. But fundamentally, everything comes down to likes repelling and opposites attracting, and the direction of the magnetic fields, interactions of the fields, right? So yeah, that is a little more thorough, if you will, analysis of that. Magnetic deflection of an electron. Let's show that guy. My own version of this too, but I might just show this one quick. So this is similar to what you've seen. It's just different setup of this, but there's an electron beam coming in, and then as magnetic fields are applied, so picture this being electrons going to the left, right? And so point your thumb to the left of your left hand, and then you can predict which way the magnetic field is here, right? It would be into the page. And so then now your palm, if you extend your left hand, thumb to the left, your fingers away from you, your palm's facing up of your left hand, and so the push is still up, right? And so you can see the force is pushing those electrons up, right? So that is, this is a link to how cathode ray tube old school TVs work. And that right here, magnetic force, I'm going to go CRT TV here. CRT. This is a video I made showing exactly that. And I'm going to turn my volume up because I explain it in here. Dude. Sorry, I'm just going to pause for a sec here because volume's not doing volume things. All right, hopefully you can hear this. If not, just click on the YouTube link and watch it yourself later on, of course. But all right, I got a little electromagnetic force or motor force demonstration for you. So I got an old school cathode ray tube television, which shoots electrons towards the screen. So I've got electrons traveling. That's going to be the direction of my thumb with my left hand. And then I've got a magnet here, nice strong one. You can tell that direction, like that, is the north. So I'm pointing north. So when I point the north in, right here, is the north. So when this north is here, you can see the norths of the compass is facing or repelling from it, right? So that's the north. So I'm pointing north that way. So we can predict what will happen here. I've got a north pointing that way. That means the north magnetic field goes around like this, right? So in where the electrons are traveling, the north is pointing that way. This messes me up and other people up, I'm sure. So the north is coming out. And then inside the television where the electrons are traveling, the north actually turns and goes around to the south on this side, right? So the electrons coming in are seeing a north facing the opposite way of what this magnet is facing. Like we're facing it to the right. That north sweeps around and affects the electrons as it's going to the left inside. Okay, so watch for the explanation here. So that means I've got electrons flowing towards you. I've got the north towards me, towards the left side of your screen, and then inside the TV, right? Push is going to be up, and so you're going to see the electrons go up. Okay, so the electrons were landing in this area, making specks. Instead, now they get pushed way up here, and they're landing up here now, leaving this big black space. So there's no electrons landing there anymore because the magnetic force deflected them up, right? And so there's plates inside of TVs like this that push and pull on electrons to make them land in certain spots to draw the picture of what you're watching. Okay, this is a super old TV, black and white, so simpler. The newer versions of these old style TVs would have, of course, little clusters of red, green, and blue, which electrons would land on and light up, and so on. They're going to land up from where they were instead of where they were headed. And so you can just move this around and direct electrons anywhere you want, which is exactly how the old school TVs worked. adjusted electric and magnetic fields to direct electrons to this particular spots to make this the picture. There you go. So that here. Then the electron beam, the massive electron thing, circular electron. I think I've kind of already seen that, but why not? Circular electron. And like I said before, about finding the mass of an electron. Whew. Don't need the sound. There we go. I don't know if it's any different than I showed you before, but yeah, get this circle, right? And so you can measure, and you know what voltage you applied, so you know what speed it's coming in with, and so on. And so you can actually determine the mass of the electron. So yeah, not much extra there. All right, so sanity check here that I've got this thing going. Yeah, okay. Sometimes I forget to unpause. So with electric motors, okay, so this one here is going to have a link for my video, but I'll have to come back to it. But so this simple DC electric motor, so this is going to be like the homemade demo that I'm going to show you a video of. But we can analyze this out here. Okay, so we've got a loop of wire, and we've got magnetic north and south nearby, and then we have what's called a split ring commutator. Okay, and so right now we've got, it says electron flow, so we're going to use left hand analysis because it says electron flow. So we're going to use my left hand, and it's going to have my thumb's going to be, point your thumb in the direction of this right here toward the end of the page like that, and then extend your fingers north to south. And so right now my hand's in front of me, my thumb's pointed away from me, my fingers are pointed to the right, my palm is facing up. That's this, right? So it's going to magnetic force up. So right away, this thing's going to want to turn this way, right? Based on that force. On this side, you have to point your thumb. You have to contort your body here, but you have to point your thumb towards yourself, and then so it's not actually that bad. It's just if you try and rotate your hand from the previous position, you might get kind of messed up. But yeah, point your thumb towards yourself, fingers left to right, and so to the right here, and then now the force is down, right? So on one side of this loop, you got force up. One side, the other side of the loop, you got force down, and so it's going to work together and make this thing rotate clockwise, right? Once this thing rotates around, then notice that this part here, the split ring commutator, is attached to these wires, and so this rotates around with it. And then once you get past 180 degrees or past the turn here, this round piece, the commutator, is connected to that brush now. Right, so they call these the brushes because they brush against the round thing there, the contacts, and the round thing, the contacts, are called your commutator. This is just the basics of how electric motors work. So they're actually pretty simple. And so let me just go find my video. I'll just pause for a quick sec here. All right, here we go. So this is a homemade model. Okay, so I actually cut a piece of wood, drilled holes, put dowels in, just bent a piece of plexiglass. This is completely homemade, and little nails there as the axle, or whatever the axis for this thing to rotate on. And so this is the coil of wire. And so the coil of wire literally just ends here and it's bare there, goes round, around, 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 and then ends here and it's bare there. So that's your commutator, the contact here and there. And then I just have a wire here that's coiled and brushes against that side, and a wire here that's coiled and then spring loaded kind of brushes against that side. So those are your brushes, just wires. And then your commutator is just the bare copper wire on each side of that little shaft there. The rest of the wire, of course, is coated with this green varnish, right? That's insulator, so the electrons are forced to go round and round. Then you've got magnets on either side here, and then voltage is applied. Okay, so I'll let my video do the talking after this. All right, here's another design of a basic motor. I've got the negative lead coming into this side. This wire goes around and around and around like that, and then back out the other side. And then the wires for the feed just go up and brush against the side. They actually call them brushes in actual electric motors. And so it's just obviously it is a real motor, but I mean, it's not very functional. But we've got the north going that way. So I've got north going that way. I've got the electrons going this way. So on this side of the coil, I've got to push down. So when I turn electricity on, and I'll just pause for a quick sec there too. So analyzing that we have a push down on this side. The other way you can analyze this, it's kind of better in the other version of the model, but you could actually curl your fingers in the direction of the coil, and then put your fingers, your thumb in the direction of the north, and so on. So there's different ways you can analyze. So this coil here, you'd say, okay, what direction it's going to make? It's going to be a north. It's just not lined up well to decide which way it's going to go, I guess. But really, you'd have a north here. If you had a coil like this, electrons flowing, you'd have a north up like this. That's going to attract to this south, right? So again, it's going to make it want to turn. But again, it's this one's set up better for the analysis of individual, like this wires right here, this like I did in the video. I've got to push down. So when I turn the electricity on, I can give it a little kick, and it runs in the direction described. Yeah, maybe the magnet's closer, amperage more, things like that, it would run faster and faster, but obviously works quite nicely. Go. So that's all right, my little homemade motor. Don't want to do that. So that is, I'll put a link in for the YouTube video, that one. And then this one's electric motor model 2. So I'll analyze this first, actually. So this one has a big coil of wire, and it spins like this, right? And so this one, again, is better suited for, curling your fingers in the direction of the coil, and then saying, okay, that makes a magnetic north this way, let's say, which would then repel from this north, and so on, right? So let's analyze this. We got electrons coming along into here. Electrons go along here. They go up and back, down in front, up and back, down in front. So I'm going to curl my left hand because I got electron flow with my, my palms facing me. My fingers are curled towards me. My thumb's naturally pointing this way, as I said, right? So it's going to make a north and want to repel from that. Okay, so this is model 2 here. Motor 2. Here's another electric motor. We got the negative terminal coming into here. So electrons are flowing. They're going down this brush here, hitting against that commutator. You can see it's a split ring commutator. It's half and half. So right now in this position around here, we've got electrons going around and around like that, which means the left hand would have electrons going around and around like that. The thumb would point to the left. So it's going to be a north over on this end. And so that's going to attract to that bar, because this one over here you can see is a south. And then the switch comes, right, where it switches direction. That's going to become a south over on the back end. And so it's going to push away. So this thing's going to want to turn clockwise from above. So if I just get contact going here and give it a little flick with my thumb, hopefully I can do this one-handed here. All right, same setup. It takes 2 hands. So there it goes. If you adjust the timing of the switch, it can work better and better. This little electric motor. So that one's purchased from like a science supply company, but again, it's just nice to be able to like see the workings, right, of how electric motors work. So this one's designed to be able to rotate and think about it. So like when you get to this portion, it's it's still spinning, so it just carries to there. Now it's just making a north here, so it's repelling. And goes, still making a north, still making a north. Now that north is attracting to there, still making a north. It's spinning, so it keeps going, right? And so now it connects the opposite way, and again makes a north there, and so on and so on. Okay, so that's the idea of these slides here. I used to have it on an overhead projector, actually, with cellophane, or the transparencies and so on. But yeah, there you go. Actual motors have several of these, right? And so you have a whole bunch of them. And so your brush comes in and hits against more than one of these. And so there's always going to be an attraction or repulsion. It's going to kick in as soon as voltage kicks on. Obviously, like these motors, if you just have one chance, there's a one connection or whatever, then if the motor was sitting like this, nothing would happen when you turn the power on, like on my demos. But as soon as you give it a kick, this kicks in, and then it goes, oh, there, and now you can go, right? Actual electric motors have many, so that they're better at starting on their own. I just had my winch apart on my Jeep to fix the brake mechanism on it, and the armature looks exactly like this kind of thing, right? This is the armature, the windings, there's the commutator, and so it's a multi-spot commutator, and then these stack two things here. These are where like a north would be created here by the electricity, so that would repel or attract from the norths and souths that are surrounding that. This as an electromagnet, right? So you have permanent norths and souths near it to attract and repel from it. All right, so there's the basics of electric motors. You've got the commutator to be able to switch the current. You've got the brushes to actually contact and direct current through places, electron flow or current, whichever. You've got the windings, of course, to make the magnetic field that's going to then attract and repel to the permanent magnets near it, and so on. Okay, and then kind of neat two little weird examples here. Okay, so there's two other weird examples that I want you to sort of think about how these work. And I want you to put your explanation in the practice assignment up here. So some basics about electric motors, 1, 2, 3, 4, and then analyzing how this one works and how this one works. Okay, especially this one here, really weird. This is a video that came out a while back, like probably 15 years ago or more. And my brother-in-law and I showed it to my brother-in-law actually at Christmas in Sudbury, and I was thinking about how it works, right? Trying to figure it out. And he's a U of T grad engineer, so works as an engineer, civil engineer, I think. He likes concrete. Anyways, and so we were analyzing this, and as I was talking about electron flow in here, so left-hand rule, he was really weirded out, if you will, or not comfortable with the idea of me using a left-hand rule for electrons. He was very much programmed, right-hand rule, current flow, and so he didn't trust basically that it would actually work analyzing based on a right-hand rule. So, or left-hand rule, sorry, but it does, of course, it correctly. I figured it out, and we came to an agreement about how it works and so on, right? I'm just more in the theoretical end of physics, so. Anyways, so this right here, this is, let's do simple DC motor. Let's do the Russian guy because he's funnier. Hopefully this link still works. If not, I'll find my version of it. There we go.
What's up, everybody? Welcome back to my laboratory. Safety is number one priority. And today we're gonna do a simple model. I'm gonna find it, tilt it a little bit, and it splits up. You guys wanna know how to do it? Let's get to it. Things you're gonna need.
All right, so you can watch the rest of the video. I'm just gonna leave it there. But you've got loop, 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 and then one end goes there and one end goes there, right? And you've got half of one, like the top half stripped on one, and actually, I guess it's the, I don't know, whatever. You got part of the wire stripped, right? Only half of the wires are stripped. So current only flows when those stripped sides are facing down, right? So the bottom side, let's say, is stripped on both of these, okay? So analyze how this could work. That one's not too bad to do. This one is weirder. So this guy here, most simple motor in the world. I'm gonna do this in my video here version because internet again, most simple. Not working so good today. Most simple motor in the world. This one's weirder to analyze for sure.
What's up, everybody? Welcome back to my laboratory. Safety is number one priority. And today I got some new magnets. That's like strongest magnets in the world. And I got like 10 of them. And we just need one piece. This is like a super magnet. So you can really break them apart that easily. really stone. And today I'm gonna show you how to make very simple motor using just battery, screw, small piece of wire, and electric tape, a little bit of electric tape, and of course neodymium magnet. So first thing we're gonna do is get our battery. I have a AA battery that will work, and grab our wire and put it on top of it and tape it with electric tape.
Or just hold it with
So
your
it
finger.
will not burn your finger. Just don't matter, like that. You see, we have the battery and a wire coming out like that. Then grab a screw and put the neodymium magnet on the bottom. Bounce it so it's like in the middle. You see what I'm saying? Then you're gonna put the screwdriver on top of the battery like that, on that thing right there. And then grab a wire and touch the magnet. Guess what happens?
Spin, spin, spin.
Little bit of smoke. Pretty cool, huh? Very simple model. Let's check it out. Look how fast it's spinning. You see it's still spinning. And just hanging there. It goes even faster. I wonder how much energy it's producing.
So I wanted to get to that part at least so I could comment on that. But so the wire touches here, and so think about whichever direction things are going here. But it could be electron flow in and so on. How the heck, right? So you have to maybe look into like what the magnetic field looks like for these magnets. I believe it would just be north, south, straight up or down. So that and yeah, see if you can analyze why this thing spins. So a couple things about the video. When he said the screwdriver, he just meant screw, obviously, language barrier or whatever. It works better if you try this on your own. It works better if you just use the flat end, the big flat end, right? Rather than having the screw have to balance in that tiny little spot. Doesn't matter which direction the electrons are going, so you could use the big flat end. When he comments about how much energy, I wonder how much energy it's producing. Well, it's not producing any energy. I think he meant, I'm wondering how powerful it is, right? It's really consuming energy, of course. Yeah, so challenge you to see if you can figure out how it works. Go through the process that I went through uh, 15, 20 years ago, whatever it is now. Literally from scratch, looking at this thing. Okay, I should be able to figure out how this works, right? So you should too. Homopolar. I can find homopolar motor. This is a little more serious looking video of this, right? Oh, there's different versions. There's all sorts of different versions maybe you could look at and play around with. But I was so loud. I was intending just to think about the main one here, but anyways, a bunch of different ones apparently. There's go. That's the main one I was. I want you to think about. Okay. So there you go. See how it goes. And then there is also, oh yeah, there's an extension here, the homopolar roller thing. Let me see if I have that ready here. Homopolar roller, slow motion. Right. That's not going to be a video, is it? Not sure if that's a video or not. Apparently it is. There we go. So kind of a neat thing, and you can analyze how these work as well. This is the explanations are in the assignment solutions, of course. But I want you to try and figure it out first. With this guy here, you have the magnets on each side, and then you go and put this little hooked wire. I've tried all these things; they all work. Not great, but they work. And it literally just rolls along the table. It's kind of funny. I think it got close to a metal bottle there, so it twitched. But yeah, so basics of electric motors was the goal today, and so not a super theoretical, heavy-duty lesson for you, a little bit of a break, but I do want you to have a chance to try to figure out how this guy works. Cool. All right. I will see you next time. Thanks for watching.